All right, let's do some momentum examples then to finish out this chapter. I'm going to do a couple inelastic problems. You can kind of see those are a little bit simpler. And then I will show you an elastic collision where we conserve both momentum and kinetic energy. And I'll show you why those are a little bit trickier and how the algebra gets a little bit nastier. But I will also show you a shortcut for them that you can use in the future. So yeah, let's start with the simple inelastic cases first. So we've got this problem here. We're saying a 2,500 kilogram truck moving at 32 meters per second hits a 900 kilogram car that's moving at 27 meters per second in the same direction. So you basically just have a big truck rear-ending a smaller car. And so we're going to say then if they stick together, what will be their final speed? So it's just very simple conservation of momentum, right? We just have to add up their momentum before and their momentum after, right? So in our case, the momentum before, right, we have the truck, the mass of the truck times the speed of the truck, right? It's all moving in one dimension, so we don't need to worry too much about we have to, make sure we pick a direction as far as positive and negative goes, but in this case, they're already both moving in the same direction, whether that's to the left or the right doesn't really matter. So we can go ahead and just keep everything positive. So we'll just have m1 v1 plus m2 v2 equals m1 plus m2 times v final, right? So again, they each have their own individual momentum before, afterwards they stick together, so they're moving together with the same speed, right? So we can simply solve for v final. This is going to be equal to m1 v2 plus m1 v1 m2 v2 divided by m1 plus m2. If you plug our numbers in, right, we're given all these. We have the mass of the truck, we have the speed of the truck, we have the mass of the car, we have the speed of the car, divided by their total mass. And what you should get is a final speed of about 30.7 meters per second, right? So essentially, right, what's happening here, we have our large truck. It hits this smaller car. The truck slows down, right, which should kind of make sense a little bit. It's kind of running into something in front of it, so it should be moving slower. However, the car is actually weighs enough such that the truck pushes it forward even faster than it was going before, right? So that's kind of what we're saying. They were both kind of going in the same direction, and the truck hit it. It slowed down relative to the truck, but the car itself was actually sped up by this collision. Okay, so that's just a very simple case. Inelastic collision in one dimension, right? When we have two objects that stick together, we basically use this same formula every single time, and it should be relatively simple. Okay, so let's look at an inelastic collision then in two dimensions. So now we're going to say we have a football player has a mass of 90 kilograms and is running at 9 meters per second straight towards the end zone. We also then have a 110 kilogram defender running at 7.5 meters per second perpendicular to the first player, and they tackle that player, right? So we have two people coming in. We have someone moving in like this, right? They're running towards the end zone. And we have another player who's going to come in and tackle them. So what we want to know is what is their final velocity. So again, this guy grabs or whatever, and they are going to go off in some direction like this, right? And so we want to figure out how fast are they going and exactly kind of, what is that angle that they are moving at. So again, we still have just conservation of momentum, right? It's an inelastic collision. So we do not have to worry about conservation of kinetic energy. So for the inelastic case, then we still do have to worry about, right, our momentum is a vector. So now we do have these two dimensions we want to take into account. So let's write our conservation of momentum for the x direction. What's that going to look like? Well, in the x direction, we just have this one player here, right? Just this person here moving, I guess, to the right. We didn't really specify are they moving to the right or the left. We just know their motion is perpendicular to the motion of our first player, right? This one's going down the field. This player is going across it. So in the x direction, though, we just have only momentum from this second player, actually. So I'm going to say we have m2 v2, and then afterwards, what do we have? We have some sort of momentum in this direction, right? So what we're going to say is we have m1 plus m2 times v final in the x direction, right? Both of them are now going to be moving together as one object, right? They're stuck together. They're moving off at this angle, and this here would just be the x component of their final velocity, right? That they would be moving at. So they'll be moving together, and then whatever this component is that we have here, right? And then this would be our y component up there. So this is in the x direction. In the y direction, we have something very similar. We have just this one player moving initially. So we have m1 v1 equals m1 plus m2 times v final in the y direction, right? So now with this, we should have enough information. Hold on a second. Let me see if I can focus this a little bit better. Okay, that might be a little bit easier to read. So we have, in this case, we can solve for just each of these individually, right? We have everything we want to know here, except for this v final in x. We have everything that we want to know here, except for this v final in the y. So we have, what is it, v final x is equal to m2 v2 over m1 plus m2. V final in the y equals m1 v1 over m1 plus m2. So v final in the x, actually turns out we get pretty much the same answer. It's very close if you round it. 4.1 meters per second, and also 4.1 meters per second in the y direction. So that tells us right away our theta, right? Since we have both x and y are the same, moving at 4.1 meters per second to the left and moving at 4.1 meters per second up, or I guess, down the field, or whatever, however we want to call it. So we have theta is just going to be, oops, not 40, 45 degrees. And our actual overall final speed will just be the square root of 4.1 squared plus 4.1 squared. So I'm a little bit off the page here. Okay, take the square root of that, and you should get your final velocity to be about 5.8 meters per second, right? So yeah, so initially we can see that they both had roughly the same momentum, right? We have a little bit smaller player running a little bit faster, and then a little bit heavier player who's running a little bit more slowly. So you have not quite exactly, but it's very close to the same amount of momentum in the positive y direction that we have in the positive x direction. So it kind of balances out. We end up moving basically just off at a straight diagonal from where we were, right? So then, of course, they'll hit the ground and they'll stop running. They're probably not going to keep their balance after this, but initially, right after that impact, right after that collision, they'll be both moving together at about 5.8 meters per second off at that angle, right? So yeah, so the same rules still apply, right? When we are doing these inelastic collisions in two dimensions, right? You just have to have, you're conserving the momentum in the x direction and you're conserving the momentum in the y direction. Okay, so let's now finally take a look at one of these nasty elastic collision problems. So it might seem like a simple problem at first, but we'll kind of see exactly, we'll get into the gritty details of exactly what is going on here. So let's see. So in this case, we have a hockey goalie saves a shot by blocking the puck such that the puck bounces off of him elastically, right? So we have, the puck coming in this way. Then we have our hockey goalie who's going to save it. So this is our before picture. The puck has a mass of 0.15 kilograms, an initial speed of 35 meters per second. The goalie has a mass of 75 kilograms and an initial speed of negative 0.5 meters per second. So essentially what we're saying is the speed of the puck is positive, the speed of the goalie is negative, so the speed of the goalie is moving forward a little bit. And then afterwards they're going to bounce off, and we don't exactly know how they're going to be moving afterwards, right? We have a 0.15 kilogram puck and a 75 kilogram goalkeeper, right? So you can probably imagine the puck's going to bounce backwards, but is the goalie going to be moving forward or backwards? We're not really sure. So this is the initial picture. They're both coming at each other. We know that, but after, we don't really know. So that's our job, to figure out what are the velocities of both the puck and the keeper after. So this is just in one dimension still. So we know that, the positive or negative will be all we have to worry about for our direction. So afterwards, the puck is going backwards, and then the keeper is doing something, right? Did this puck have enough momentum to actually knock him backwards? It's going to slow him down at the very least, but we don't really know yet if he's going to be going forwards or backwards, but we will be able to figure that out. Okay, so let's write down our equations that we need to then use, right? So since it is an elastic collision, we conserve our momentum, so we'll do that one first. That's the easy part. So we'll say we have mass of the puck times the speed of the puck plus mass of the goalie times the speed of the goalie. So as I have this written, I'm just going to keep everything positive. Then this I would plug in a negative number into this term here, into this VG, right? Um, and so then this is our momentum before, and our momentum after is going to be mass of the puck times V of the puck after plus mass of the goalie times V of the goalie after, right? So this is our conservation of momentum equation again. We know all of these values over here, but we don't know these final velocities. So we have one equation, two unknown. So of course, we do need to conserve our kinetic energy as well. So what would that one look like? You'd have 1/2 mass of the puck, V of the puck squared, plus 1/2 mass of the goalie times V of the goalie squared is equal to 1/2 mass of the puck, V of the puck after squared plus 1/2 mass of the goalie, V of the goalie after squared. So I'm just using these primes again to denote that this is the speed of each thing after the collision, right? And then it's the speed of the puck and speed of the goalie. Okay, so we have that. And so now we can see, technically, this works. We do have two equations and two unknowns, right? But if you start to try and do this, you'll get, you'll start kind of catching yourself up very quickly and see how complicated it can get. So if you just do it the normal way, right, just, isolate one of your variables and plug it into the other equation, this is what you end up with, right? You have your V of the puck, right? So let's go ahead and let's solve for that, and I'll kind of show you the problem with doing it this way. Your V of the puck prime must be equal to what? Well, we're going to have all of this stuff first. P VP plus MGVG minus GV prime, right? So I subtract this over here, and I divide the whole thing by max of the puck. So now in theory, I could take this V prime, V of the puck prime, and I could plug it into this spot here, and then I have to square this whole thing, and then I would end up with terms where I have VG prime squared, but I also have some where it's just VG prime. You'd end up with a very enormous, very nasty looking quadratic formula that you could, in theory, solve. From a practical standpoint, it might take you a while. You might not want to actually try and do that. You'd probably lose some terms. There is a slightly easier way to do it, and even the easier way to do it is still going to be lots of algebra, but I will show you exactly what some little shortcuts that we can do to make this a little bit easier. So let's rewrite our two equations. So we still have these two equations, right? We have our conservation of momentum, we have our conservation of kinetic energy. Let's rewrite those and see how we can kind of simplify these things to make it a little bit easier. So again, we have plus G equals PVP prime plus MGV G prime, and we have 1/2 MV squared plus 1/2 GVG squared equals 1/2 PV P prime squared plus 1/2 MGVG prime squared, right? So these are two equations. We can rewrite these though, and we're going to divide them by each other after we rewrite them. So let's go ahead and gather all of our. Let's simplify this one a little bit. This first one. Let's rewrite this way. Let's take this term and subtract it over here, right? Take this MP VP prime term and put it over here. And then we're going to take this MG VG term and subtract it over here. So we're going to put all of our puck information on one side, and we're going to put all of our goalie information on the other side. And what we end up with is something that looks like this. VP minus PVP prime. And then this is equal to MGVG prime minus MGVG, right? So we can simplify this a little bit more, right? We can kind of factor out these masses. This is why this is helpful to us. So you have MP times VP minus VP prime is equal to MG times VG prime minus VG, right? So this is still just our conservation of momentum equation, right? I've just kind of reorganized where the terms are. So we can do something very similar with our conservation of kinetic energy equation, we can cancel out all the halves. And if we move our puck terms over and our goalie terms over in much the same way, we end up with, so I'm going to call this equation 1, right? Equation 2 then becomes, so just to be clear, this is equation 1, this is equation 2. I'm just rearranging these terms. So equation 2, then we can do this very similar thing, put all our puck terms over here, cancel out the 1/2, and we end up with this. So now these look sort of similar to one another, right? They do have something in common that we're going to see here and we're going to exploit very soon. So if we remember from algebra, right? So we have, here's our terms here and our terms here. If you remember from our algebra, right? When we have something like a squared minus b squared, it's called difference of squares. And what you see is that a squared minus b squared, if you remember like your reverse FOIL and all this kind of stuff from your algebra classes, you can say that this is equal to a plus b times a minus b, right? So what I'm going to do is we're going to then divide our equations by one another, right? I'm going to take equation 2, I'm going to divide it by equation 1, right? So basically the left side of equation 2 gets divided by the left side of equation 1, and the right side of equation 2 gets divided by the right side of equation 1. And that's fine to do, right? Because again, the whole point is that these are equal. So if I'm going to divide this side by something, I have to divide this side by the same thing, but I can still do it in a different expression, right? And so what I end up with is this. The masses will all cancel out. Then this term here, this is my a squared minus b squared term. If I divide out a factor of a minus b, right? Here's my a squared, here's my b squared, here's a, here's b. What I'll get is just a plus b. So by taking this, dividing out these equations, what I end up with is this. I have vp plus vp prime equals vg plus vg prime. So this is actually a pretty important result. Let's rearrange this and I'll kind of show you in general what this is actually conceptually telling us, because it's actually telling us something very important in general about these elastic collisions. I know I'm doing it for this very specific case, right, where we have our hockey puck and our keeper, but really I haven't plugged any numbers into this, right? I just started with just the general equations, we're just conserving momentum, we're conserving kinetic energy, and what we get with this kind of little clever rearranging of our terms is we get something that looks like this. And so what I can do furthermore is I can say this. I can say Vp minus Vg equals Vg prime minus Vp prime, right? Another way to write this is the same equation again, just rearranged a couple different times. Vp minus Vg is equal to minus Vp prime minus Vg prime. So what is this conceptually actually telling us? Why is this such an important result? Look at what these terms are saying, right? All I did here again was I just subtracted over Vg and then subtracted over Vp prime. So I've got my speeds beforehand, right? And these are somehow equal to this thing that looks very similar. It's not quite the same though. I have the velocity of the puck before minus the velocity of the goalie before has to be equal to the velocity of the goalie after minus the velocity of the puck after. Or again, we can say the difference in speeds between the puck and goalie before has to be equal to the negative of the difference in speeds between the puck and the goalie after. This is actually a very important conceptual result for these elastic equations because what we're really saying is, right, if we think about it, what it looks like from the goalkeeper's perspective, right? We go back to our relative velocities, right? This is essentially kind of just a relative velocity thing. I'm looking at the difference in velocities between the puck and the goalie. So in some sense, you can think of it like this. Before the collision, the goalie is moving at some speed and the puck is moving at some speed. But the goalie is going to see the puck coming towards him at what? He's moving towards it at 0.5 meters per second, right, relative to the ice. The puck is moving at 35 meters per second relative to the ice. So before the collision, the goalie is watching this puck close distance on him, and as far as he's concerned from his point of view, the puck is moving at 35.5 meters per second, right? And that's what this represents here. So you have Vp minus a negative 0.5, right? So that's what what it is before. After the collision happens, right? if we look at what the goalie sees again from his perspective, is he will see the puck moving away at exactly 35.5 meters per second. So initially, if you look at the relative velocity between these two objects, right, however they're moving, right, whenever they collide elastically and then move away from one another, what you're going to see is that the relative velocity between the two objects does not change from the before to the after, right? So again, whenever two things collide elastically, the difference in velocity beforehand is equal to the negative of the difference in velocities afterwards, right? So essentially, again, what we're saying is if they close in towards one another at a relative speed of 10 miles an hour, they bounce off, they move apart from one another again, they will be moving towards each other at 10 miles an hour, they will collide, and then they will move away from each other at 10 miles an hour. Now, exactly which one's moving which according to our rest frame, in this case, the rest frame of the ice, that can be a little bit tricky, and that's going to depend upon the masses. We're going to have to do some more algebra to actually fully solve this. But for now, we can say that this is a very important general result. So let's go ahead, let's finish this up. Let's use this, right, along with our conservation of momentum equation, and we can actually kind of solve that system of equations, and that will be a little bit easier. So now the two equations that we want to use would be some form of this one right here, and then again our conservation of momentum. So I'm going to rewrite that one as well. So we'd have mp vp plus mg vg equals mp vp prime plus mgv g prime. So now again, I still have two equations, two unknowns, but I was able to divide out and get rid of this some of these squared terms. So this is also just a valid equation describing the situation, right? This is just kind of a natural consequence of an elastic equation. So it's not strictly conservation of momentum, it's not strictly conservation of energy, but when I combine the two, I get this piece of information. So with this, I still have some nasty algebra to do, but it's not nearly as bad as trying to do it with these squared terms or anything like that. So let's go ahead, let's solve for our VP prime, for instance, and then plug it into that one. So I can rearrange this slightly. VP prime, right, from this one ends up being VG plus VG prime minus VP, right? So now this we can take and we can plug into our conservation of momentum equation and go on from there. So again, the algebra is still not great, but it's not nearly as bad as it could have been. So what does this end up? If I take this, if I actually plug in my equation for VP prime and put it into my conservation of momentum equation, what I get is this. The VP plus mg vg is equal to mp times vp prime, which I know vp prime is vg plus vg prime minus vp plus mg vg prime. I know I'm using mg a lot, but remember this is just a subscript. We don't have any force or any gravity going on here. This is just the mass of the goalie is all I mean by that. So now we have this, and so now we finally have one equation and one unknown. Again, you have to do some rearranging, but it's not, there's no squared terms, so we don't have to do any quadratics or worry about anything like that. So let's go ahead and gather our terms together of this VG prime. So MP VP plus MG VG equals MPVG plus MPVG prime minus MPVP plus MGVG prime. So now here's my two VG prime terms. We'll move everything else over to this side. P plus G VG minus MPVG, right? So that's coming from there, plus MPVP. So that one comes over to this side, right? This one becomes a minus, this one becomes a plus. Collect the VG prime terms equals VG prime times MP plus MG, right? Okay, so now we can divide this over and simplify that out, and we will have our expression for our Vg prime. So as it turns out, Vg prime, the velocity of the goalie afterwards, is going to be this. We have two MP VPs, right? Here's one, here's the other, plus mg minus mp times vg, right? And these two terms together, they both have a vg in them, so I'm pulling that out. Mg minus mp, and then we divide this whole thing by the total mass, mp plus mg. So this will actually work in general, right? In this case, again, I'm doing it for the goalie and the puck. But again, these are just subscripts for now. If you just treat it as object 1, object 2, right? Object 2, in this case, I guess, if you call the puck object 1, this would be the speed of that object after for any sort of elastic equation that you have. So again, make sure to plug in the correct values if it's positive or negative in here, and you will get the correct positive or negative value for this Vg prime. In this case, if you plug everything in, you do get a negative value for the goalie. You get negative 0.36 meters per second, right? Okay, so with this, what we know again from our other result that we derived from here, we can figure out very quickly, right, what the velocity of the puck has to be afterwards, right? We figure out what the velocity of the goalie is afterwards, but we can also derive that in general. We'll get something very similar. Vp prime will look somewhat analogous to this. We've switched some terms around. But if we were to go back through, you do all the algebra, but you solve for Vp prime instead, what you'll get is this. P minus mgvp plus 2 mgvp. Whoops, no, this is 2 mgvg. This is a vg. This is the speed of the goalie beforehand, just so we're clear. Not a p, this is a g. So then we again though divide by the total mass. And in this case, what we get for this is what we would expect is a speed of negative 35, right? And again, make sure to keep track of all your minus signs. Negative 35.86 meters per second. So we can see here that if you take this and you subtract the two from one another, what you will get is a difference in velocities of negative 35.5 meters per second, right? Which again, just as what we started out with, we also had the case of our initial velocity difference was also 35.5 meters per second, right? 35 minus a negative 0.5. The goalie was the puck was moving towards the goalie with a speed, right, a relative speed of 35.5 meters per second. After this collision, the goalie is actually still moving the same direction that he was, right? The puck has bounced backwards, and it's actually bounced backwards faster than what it was moving beforehand, whereas the goalie is still moving forward as far as he's concerned, right? It's backwards in our reference frames to the left in my reference frame. So it is a negative number. But from the goalie's perspective, he's still moving that same direction. He's just moving a little bit more slowly, right? But we still do, again, have that same overall difference in velocity. They used to be coming towards each other at 35.5 meters per second, and now they are moving away from one another with a relative speed of 35.5 meters per second, right? So these results here are very important if you understand what they mean in general, right? Again, I used it for a goalie and a puck, but if you want to use it for any two objects, make sure you keep track of the subscripts, make sure to keep track of, kind of where this all came from. But there are some homework problems that you'll do that are like this. Again, this is you don't have to do the whole derivation. You can skip to just using these formulas. This is for one dimension. You do have a homework problem that you have to do something similar to this. It's not as bad as this in 2 dimensions, but I will also give you a hint to get started on that one as well. So yeah, so that's kind of our different types of collisions that we can have with our momentum, right? In inelastic collisions, we're only conserving momentum. Those tend to be much simpler to solve. For the elastic cases, we are also conserving kinetic energy, right? Which means we have more information available, and so I can give you less information to try and solve the problems with.